Hi guys, today's LeetCode Daily is number of ways to arrive at a destination. So we are given a city that has n intersections which are numbered from 0 to n minus 1, and between some of these intersections there are y-directional roads, and it is given that inputs will be given in such a way that we can reach from any intersection to any other intersection, and there will be at most one road between any two intersections. Now we are given 2D integer array roads where roads of I is ui, vi and time I. It means there is a road between intersection ui and vi, and it will take time to travel from ui to bi. Now we have to find out how many ways we can travel from intersection 0 to intersection n minus 1 in shortest amount of time. And this answer can be like large, so we have to return it by doing modulo with 10 to the power 9 plus 7. Now we'll see example to understand this question in a better way. Like here we are given that there are seven intersections, and these are like roads between intersections. So this we can visualize as a graph. Like intersections we can represent as nodes and roads as edges, so this will convert to this graph. Now there are seven intersections, so there are seven nodes numbered from 0 to 6, and there are roads between some of the intersections, so we have connected these nodes with that roads. Now we have to find out how many ways we can travel from 0 to 6. So if we'll see, like, in shortest time, the important is we not only have to give the count to travel between 0 to 6, but also we have to tell it should travel in the shortest amount of time. Like if we'll see this path, it will take 7 minutes. This will also take 7 minutes. If we take this path, it will take something like 3, 3, 6, 9, 10, 12 minutes. So this is, and this path will also take 7 minutes, and this path will also take 7 minutes. So like minimum time we'll need 7 minutes to go from 0 to 6, and there are four such paths that will take 7 minutes. So we'll return 4 as our answer. Now we'll see approach how we can do that. Whenever we deal with shortest distance from source node to other node related problem, we always use a standard algorithm, that is Dijkstra's algorithm. But here, like, we have to also calculate path count for traveling from 0 to n minus 1. So in this question, like, we also need to use DP also. But don't worry, like in DP, in the name of DP, we are just using one small vector path count, and that we'll see how we can use it. Now we'll we briefly revise Dijkstra's algorithm so that we can use this in our problem. So initially we'll take distance array where distance of I will store distance of node I, minimum distance of node I from source, and initially we'll take infinite distance of all nodes from source except the source node, because distance of source node from the source node is 0. Now we'll take a min heap and add source node and its distance in the min heap, which is 0. Now until this heap is not empty, we'll take the topmost element, we'll find node and time value. Then standard way we'll visit all its adjacent nodes and see if from the current path it is giving less distance or not. If it gives less distance, that means it is a better path, so we'll update the distance array for the adjacent node. Also we'll push it in the heap so that we can use this better path for our further calculations. Now we'll see how we can use this in our question. So in our question we are dealing with time instead of distance, so we'll take time array. Also we have to find path count, so we'll take path array where path of I will give count of all the paths which we can travel from source node to ith node in minimum time. Now, like standard thing only we are doing, we are taking the node out of priority queue. After that, for for all its adjacent neighbors, we are updating if time plus edge weight is less than adjacent of node. It means that we got a new valid path. since it is a new path, then path count of adjacent node will be equal to path count of node. But if this condition holds, time plus edge weight is equal to time of adjacent node, it means we got a new path, but this can also be used and earlier path also can be used, because they were also, from them also we were able to travel in the same time only. So this time path count of adjacent node will be equal to path count of node, because we got some new nodes, new paths, but plus path count of adjacent node, because we can use earlier path. Now we'll see code for better understanding of the implementation part. So this is a standard adjacency list. Here we are storing pair int comma int instead of int, because it is weighted graph. Now we are traversing in roads, and it is given that the roads are bidirectional. So if there is road between U to V, then there is also road between V to U. So for U we are pushing V and its edge weight, and for V we are pushing U and its edge weight. So after this array, we'll get adjacency list. Now we are taking time vector. In this, we'll store the minimum time needed for traversing each node from source node. And here, this is path vector. Here we are storing the count of path from source node to ith node. And initially, time of 0 will be 0. Also, paths of 0 will be 1, since from source node you can travel to source node in a one way. Now, this is min heap. By default, like in C++, priority queue gives max heap. So we need this syntax so that we can use it as min heap. Now we are pushing source node and its time into the priority queue. Now, until this priority queue is not empty, we'll take the first element, we'll take its time and node value and pop it. Now we'll traverse all its adjacent node. If for any adjacent node, the time plus edge weight is less than the time which is stored in the time vector of the adjacent node, that means we got a better path which we will help us to travel in less time. So we'll update the time vector for adjacent node with time plus edge weight. Also, we'll push this ad, time and adjacent node so that we can use further. Also, since we got new path, so we'll do paths of adjacent node, means path count for adjacent node will be equal to path count of node. Now, if time plus edge weight is equal to time of adjacent node, that means we got new path, but it is not better path. So we can use old path also and new path also, whichever we want. So path count of adjacent node will be equal to path count of adjacent node plus path count of node. After all this loop is completed and priority queue is empty, paths vector will contain path count from source node to index node, which can be traveled in minimum time. So we'll return paths of n minus 1, as we want to return path count from source node to n minus 1th node, which can be traveled in minimum time. If we talk about time complexity, then we are using standard Dijkstra's algorithm. So it is n plus e log n. If we talk about space complexity, then here we are using adjacency list. For all the elements, we are storing their edges. So it is we go of n plus e, and the rest, this is also we go of n, this is also we go of n. This is also, so overall space complexity is we go of n plus e. If you have understood this question, then please like, share and comment on this video, and subscribe my channel for more such videos. Thank you.